Okay, let's apply everything that we learned about the Laplace transform to solve ODEs with jumps. In particular, let's try to solve the following monster: y double prime plus 4y equals f of t with 0 initial conditions, where f is the following piecewise defined function. And let me draw a picture. It'll be easier to understand it that way. So f, what it does, so this is t. It starts out at 0 until we reach t equals 5. So from 0 to 5, it's 0. And then it becomes linear. So 4t minus 20. Maybe here 4t minus 20 until t equals 10. And then at 10, the value is 20. So 0, 4t minus 20, and then 20. And this has a very cool application. So think here of f as what's called a dimmer switch. Or in French, it's called gradateur de lumière. So think of f of t as a dimmer switch. It's a dimmer switch. Well, think maybe light, where it goes from 0 volts, so the light is off, going from 0 volts, and gradually turning it on, like whoop, until we get 20 volts. 0 volts to 20 volts. And then gradually. And then this differential equation, for instance, is like the mass spring equation, but where your forcing goes from 0 gradually to 20. And the cool thing is, technically, this is nothing new. We just combine what we learned about ODEs with Laplace transforms and all our jump business. So the idea is we want to take Laplace transform of the differential equation. So first we need to figure out the Laplace transform of f. And in order to do this, we need to write f in terms of jumps. F of t in terms of UC, of their Heaviside functions. And how do we do it? Just as usual, we start with 0. Start with 0. And at t equals 5, you jump by how much? So you jump by, well, technically, so the starting value is 0, and it goes to 4t minus 20. So the difference is 4t minus 20. But remember, it's important to write this in terms of t minus 5. So this is really 4t minus 5. So this will ultimately give you a plus 4t minus 5, u5 of t. And then similarly at 10. So at t equals 10, you jump by, remember, end minus start. So the end value is 20. The start value is 4t minus 20. That is the start. And then you can simplify this. Careful, that's not minus 4t. It's 40 minus 40. And remember, you have to write this in terms of t minus 10. So it becomes minus 4t minus 10. That's in order to use our formulas where the exponential term comes out. So what this implies is for t equals 10, you subtract a 4 times t minus 10, u10 of t. And so in the end, what is your function? F of t, again, you start at 0, so technically 0 plus. and 4t minus 5, u5 of t, and then minus 4t minus 10, u10 of t. Very good. And if you want, you can even check that the piecewise definition holds. And then what we can do now, we can take the Laplace transform of f, L of f of t, then becomes the Laplace transform of 4t minus 5, u5 of t, and then minus, if you want, Laplace of 4t minus 10, u10 of t. And remember, whenever you shift and jump, so t minus 5 u5, t minus 10 u10, an exponential term comes out. So that was a formula that we discussed in the previous videos. So what this becomes, it's e of minus 5s of the unshifted Laplace transform, L of 4t, and then minus e of minus 10s unshifted Laplace transform, L of 4t. You might say it's lit, but I say it's L of 4t. So here again, we used that the Laplace transform in general of shift and jump gives you an exponential term, e of minus cs Laplace of f of t. And then, well, for Laplace of 4t, use that power rule. So it becomes, I think, 1 over s squared. So in the end, it's e of minus 5s, and 4 over s squared, and then minus e of minus 10s, 4 over s squared. And you'll see this will make the rest easier if you factor out the 4 over s squared. So that equals, if you want, 4 over s squared, and then e of minus 5s minus e of minus 10s. It doesn't always factor out, in which case you just do that term separately. But here it's quite nice. All right, so that again is the Laplace transform of f. So this again is the Laplace transform of f. And then the rest is as usual. So you just take Laplace transform of the ODE. So as I like to say, you take the L. So our ODE was y double prime plus 4y equals f of t. And then you take Laplace transforms. So Laplace of Ly double prime plus 4 Laplace of y equals Laplace of f of t. Now remember, we had our Laplace miracle. So L of y double prime becomes s squared L of y minus s of y0 minus y prime of 0. I like to remind you, we have 0 initial conditions, plus 4L of y. Laplace of f, we just found. So I believe 4 over s squared, e of minus 5s, minus e of minus 10s. So if you want, again, you can factor out L of y, and you get s squared plus 4. S squared plus 4L of y equals 4 over s squared, e of minus 5s minus e of minus 10s. 10s. And again, sanity check. What is s squared plus 4? It's precisely the auxiliary equation. And so in the end, what we get, L of y, is 4 over s squared times s squared plus 4, and then e of minus 5s minus e of minus 10s. And of course, the next step is to do partial fractions, because remember, our goal is to write this whole thing as a Laplace transform. So step 2. Step 3, partial fractions. And partially fractions, but a whole lot of love. And remember, what we do here is we first focus on the terms without exponentials, and then we add in the exponential term. So here, first focus on 4 over s squared times s squared plus 4. Again, we want to partially fractate this. So this is something over s squared, something over s squared plus 4. S squared has degree 2, so you have to guess something of degree 1. So as plus b. S squared plus 4 has degree 2, so you have to guess something of degree 1. Plus cs plus d. And then, I will not do this, but you put it on the common denominator, you compare all the terms, just like we've done before. So this, the details you can see in the notes. And ultimately what you obtain is a is 0, b is 1, c is 0, and d is minus 1. Again, what's more important here is figuring out what to do with that. And what this tells you is 4 over s squared times s squared plus 4 becomes 0s plus 1 over s squared plus 0s minus 1 over s squared plus 4. And so in the end, weirdly enough, in just a coincidence, it becomes a difference. S squared plus 4. And that is good, because now we can figure that out as a Laplace transform. So now let's go to step 4. So what did we have? L of y was 4 over s squared times s squared plus 4, which now remember becomes 1 over s squared minus 1 over s squared plus 4 times the exponential term, e of minus 5s minus e of minus 10s. Now that you can recognize as a Laplace transform, so this becomes L of t, using the reverse power rule. Now, 1 over s squared plus 4, it smells like sine of 2t, but sine of 2t would be 2 over s squared plus 4. So we have to do 1/2 sine of 2t, and then times e of minus 5s minus e of minus 10s. Now, there will be some shifting going on very soon, which becomes quite lengthy. So here, I actually allow you to write this in terms of a function h. So if you let the inside to be h, then this does become L of h of t times those exponential terms, e of minus 5s minus e of minus 10s. Again, if you do that, please write down what h is. So where h of t is t minus 1/2 sine of 2t. And remember what the exponential terms do? They shift and jump. So this is L of h of t minus 5, shift and jump, so u5 of t, and then minus h of t minus 10, u10 of t. Or again, we use kind of the reverse of the formula from before. So what do we get? Laplace of y is Laplace of this monster. So the answer is y is this monster. I think step 5. Answer. So y of t is in fact h of t minus 5, u5 of t, minus h of t minus 10, u10 of t. And once again, if you do that, please write down where h is. So where h of t is t minus 1/2 sine of 2t. Box this. Now, this is very cute. Okay, we actually have this explicit formula for y. But what's more interesting is to see what happens when we graph this. So remember this analogy with this dim switcher where it starts at 0, then gradually lights up, and then becomes 10, I believe, or 20, one of those two. And you can actually see this in the graph because if t is before 5, so if you go from 0 to 5, then y is just all 0. That's just the definition of UC. And then between 5 and 10, what you see is sort of a transition period going on, where the function is kind of a hybrid between constant and sines. And then after 10, again, all those u5s and u10 are 1. And what happens is that the motion just becomes purely sinusoidal. Okay? So this is our y of t. So once again, there are 3 regimes here. One where y is constant. Between 5 and 10, y is in a transition phase. And then after 10, y becomes sinusoidal. How did we achieve this? Simply by using those beautiful jump functions. How cool is that?